we'll try to discuss types of orbits. Okay, types of orbits. Before we go to types of orbits, just something from last class. Now, this R dot, and this is velocity. You understand? Okay. Now, what you have is we have VR in the UR direction and V perpendicular in the U perpendicular direction. Okay. So if you want to pull up something. Now, does this make sense to you? See, anything we discuss, we always have three components, right? A vector is always written down as three components. Why do we have just two components here?
One is perpendicular, one is tangent.
Where is the third component?
One runs tangent.
Where is the third component?
Is it because we are only considering two like 2D? Just 2 dimensional? Or still 3 dimensional?
You have to understand that
The radial component.
huh?
The radial component.
This is the radial component. This is the
The perpendicular.
yeah. Whenever we discuss any vector, we always talk about three components, right?
No,
Yeah,
unless
it's-
it is 3 dimensional.
So where is that? Where is the third component? That's what my question is. Why are we not discussing, when we discuss velocity, why are we discussing only two components? Even position, you will see that there is only I have to you have to keep something in mind, or you have to understand this very clearly. H is conserved, right? In plain English, this is what you learn as aerospace engineering. In plain English, this means orbital motion is limited to a plane. Okay. That's what this statement means. Conservation of angular momentum means that orbital motion is always limited to a plane.
Last class clarification.
And that is the reason we have just two components. These components are the components only in the plane. There is no component perpendicular to the plane because H is conserved.
There's no component
Perpendicular to the plane because H is conserved. And what we are talking here is this is linear motion. This is linear velocity. Okay. Now, how do we define H? H is R crossed with R dot, right? If we take this VR QR plus V perpendicular.
Dr. Sunday, is this tied to Kepler's law?
Huh?
Is this the stuff tied to Kepler's law?
This is
Or is this the class before that?
not Kepler's law. This is from last class. We discussed. I was trying to give you expressions for.
Oh, I'm with you. I see. I'm with you. Thank you.
So when you do this, what you're going to get is R, VR, U, R cos Q R plus R B perpendicular U R cross with U. Okay. So this goes to 0 because it's a vector cross with itself. So this is essentially R B perpendicular R okay, which implies H, the scalar H is equal to R B. I gave you this expression last class. But I did not tell you how we got that. So what this means is, it's always, whenever you look at anything being taught in class, you have to really question yourself. So why are we doing this? What does this mean? What does this imply in physical terms? In actual. So this is all math. There is nothing physics about it. But when you interpret this, this means, where is this vector? This is a vector, right? Alright, please take a look at the slides or the projector. Focus on this figure. Just focus on this figure. What is this body?
That's the planet. Mass.
What do we call? That's the central body.
Inertial frame.
That's the central body. Okay.
Attached to the inertial frame.
Yes, that has the inertial frame. Okay. This is the orbit. What you're seeing here is, this is R. Okay. That is R, and the vector going in that R is this vector, this direction. UR is the direction, the radial direction. And this U perpendicular is it's tangential to that.
The R dot, or in the R dot direction?
R dot will have this component plus this component. This component is responsible for making sure it doesn't fall in. Okay, this component ensures it always orbits.
So that component,
If this component, see, if this component did not exist, if there is no gravity, what will happen?
If there's no gravity,
If there is no gravitational attraction, it will just go in a straight line. Okay? So the gravitational attraction will make sure this is for that. This, so if this component is absent, what will happen?
So if that component is absent,
Right.
then it won't rotate. It won't orbit.
It will just come back. So it is like throwing a stone. If
Oh,
you throw a
yeah.
stone radially, assuming everything is vacuum, right? There is no disturbance. This is what you're doing. You're pushing it radially up. If you push it radially up, once that force is ceases, it will just come down. That is this component. Okay? This component ensures it always there is linear motion. So if it will go like this, then it will go like this. So if you look at the launch, it will go like this, and then it will do that. Okay. So what you're seeing here is, see, this H cap is this.
It's a marker.
and
This is H cap. Okay.
question. And so you R cap cross U perpendicular equals 1. Correct? Because when you put H and the last equation is just HR E perpendicular.
Right?
Yes.
And this is the magnitude. If you take the magnitude, this is the vector.
Okay.
Be careful. Alright? So H is simply H vector is equal to R B H cap. And H cap is always perpendicular to the plane. Okay? This is another, if you want to just look at this. Okay. So look at this. You'll see what I just talked about. Look at figure 2.9.
okay.
Do you see R dot? So this is that same central body. This is that same path. Okay? This is where the orbiting body is at this time instant. And UR is just the radial direction. UR. That's just the radial direction. You see that? UR. U perpendicular is the tangential direction or the perpendicular direction to UR. Your velocity, your actual velocity is this R dot. Your complete velocity is this R dot. So this velocity R dot will have a VR component, the radial component, which is responsible for taking care of gravity. It will have this V perpendicular component.
And there's no H on there because it's moving in a single plane, correct?
H is always there.
Well, it's conserved because it's moving in one plane.
It's there. It's Conserved. H is always conserved. What do you mean H is not there?
I said it's conserved.
Right, it's always there. Conserved means it's constant. It is not 0. H is never 0. So when you say it's not there, it means you are assuming it's not, it's 0. It's there. So where is H? Tell me where is H?
It's coming out of the string.
Coming out of the screen. Yes. So H is just coming out of the screen. H is always there. Okay?
Wow, H is coming out of the screen where?
Theoretically.
Okay.
Huh? H is just coming out of the screen. The direction of H.
Like you talked about on the board that day, just like.
So if you put this on here, H is coming out.
Yeah.
So here, what is the difference between this one and the previous figure you saw? The previous figure was on the ground. It was depicting something on the ground. Okay? The plane is different. You see? What is the plane here we are talking about? The plane is practically the ground. So H is coming out of the ground. Here the plane is the screen itself. So it has to. And why is it coming out and not going in?
Right hand.
Right hand. So this is what this means is, see, this means that the contribution to angular momentum, the radial component does not contribute to angular momentum. That's what this is telling you. Right? You understand torque? When do you get a torque?
When you get torque.
What is required, what is most necessary for torque? So if you have torque, right? When do you get a force for this and when do you get a torque for this? If you are applying force which is going through the center of gravity of this, will you get a torque?
No.
No.
Right? So that is what is happening here. So this means the force is going through the center of gravity. The radial component is going through that center. That will not contribute to torque, or that will not contribute to angular momentum. Torque is possible only if the force is, there is a moment arm. You understand moment arm? Moment arm means the distance from the center of gravity. The perpendicular distance to the direction of force. You get it? So this is that perpendicular direction. Right? So if you apply force, gravitational force is like force, right? Gravitational force is like applying force. If that force is going through center of the orbiting body, that will not contribute to torque. That will not contribute to angular momentum. That's what this says. Only the perpendicular component will contribute to angular momentum.
So are you comparing H to the torque?
Change in angular momentum. What is change in force?
What is change?
In force? Or sorry, what is F is equal to, what do you, d over dt of linear momentum. Change in linear momentum is force. Right? That's what Newton's second law is. Change in linear momentum is force. So change in angular momentum is torque. Okay? So this is linear one, and there is one linear momentum, then there is angular momentum. So change in linear momentum is torque, change in angular momentum is, change in linear momentum is force, change in linear momentum is torque. Okay? So that's the reason, that is how you see torque and angular momentum. You get it? You can reason out, you can think about linear motion and angular motion in that sense.
So I have a question, because so the H vector,
Mhm.
you're saying that that's somewhat comparable to the moment arm in theory. But
Angular momentum, change in angular momentum is torque actually. Its torque is what? Force into that momentum.
okay, I'm talking about that specific part where we said, I'm trying to phrase it like you said it, something about this is that in this case. You were saying like the equivalence to the moment arm times the, we were saying something about the H being that in this case. You know what I'm talking about? And I think Clayton asked something. What was the question you asked? That he did, do you remember? What? Okay. Well, okay. So what I'm asking, can we go back to that H really quick?
Okay.
The H vector.
Hmm.
We can't say that the H vector is the moment arm. We can't say that in our case. So what exactly are we saying about that part that right there that you just wrote? Not the box part, but what's the significance? I'll put it that way.
This one?
Yes, what's the significance of that equation?
So what it says is, you look at these two, okay? Or look at these two. So this, you get this, right? So this is the momentum,
That's the moment arm. That was my question.
right?
Yeah.
So this momentum, the force has to be perpendicular to that force, to that momentum. Now this is in the same direction as the momentum.
Okay.
And this is not going to cause angular momentum.
Okay.
Because it is in the same direction.
Right.
This is perpendicular, so this is the momentum, which is this R, and whatever force you apply with this is going to cause angular momentum. If you apply force like this,
Nothing's gonna happen.
nothing, no moment is going to happen.
Okay.
So that is the reason this is zero.
Okay.
Okay.
Thank you.
So now types of orbits and types of conic sections are exactly the same. Okay. You recall orbit equation, okay, which is R is equal to a square over mu 1 plus E cosine theta. E here is eccentricity, okay? And this eccentricity is the same eccentricity which we talk about for conic sections. What is eccentricity in conic sections? For a given conic section, what are the conic sections? What are the conic sections we talked about? Circle, ellipse, parabola, and hyperbola. Right? So conic sections, this eccentricity defines the type of conic sections. Eccentricity is nothing but it's the relationship between semi-major axis and semi-minor axis. Okay? So this, if circular orbits E is simply 0. Okay? What does that mean?
That means we'll just keep it squared over u. R equals a squared.
Right. So now if you substitute this, right? So you're going to get R is equal to simply h squared over 2. Implies R is equal to h squared over 2. Okay. Now,
So
what? R
Cross
B perpendicular, right? So it is H square is R square B perpendicular square, or we can say this R square B circular square. This is
Be circular.
this.
Where do we circular come
This velocity is just the circular velocity.
When you have a
from? Oh,
circular.
because it's
orbit.
always perpendicular.
Right, it's always perpendicular. So this is just a circular velocity, right? It's the velocity of the circular orbit. That's what it says. Okay. So you have, if I substitute this, R is equal to R circular R D circular is equal to R over mu. This is, whenever I put something in box, it's actually very important. That is something you have to either remember or you should know how to get there. In most cases, you can what you really need to remember or what you really need to memorize is not much. Let me just take you again. So this you can actually derive it yourself. Okay? It's a very simple thing. You just need to know, you just need to understand this. So what, for circular orbits, what do you know? You have to know that E is equal to 0. Right? You memorize this, right? And then you substitute, you're going to get H squared over here. And you can say H, if you don't want to remember this, you can actually start here and derive this H.
What does E stand for again?
Eccentricity.
Well, yes, what is that again?
It's the relationship between semi-major axis and semi-minor axis of a body section. Okay. So look at this roadmap. Actually, this is a very good. This is actually in your appendix, and it tells you what, how, and where do we get. What is our roadmap for this course? It's also just behind So the second edition actually has this behind your this thing. There's a roadmap. Okay, but the third edition, you just have to go to Appendix B. Go to Appendix B. Yeah, that's a very good. That is what the course is about. So this, you remember, what is this?
That's force equals.
Can you email us this PDF so we can take a closer look at it? I'm just wondering. I don't know.
Okay, send us the PDF.
I'll be in trouble if I send you the PDF.
Oh, you will?
Yeah, because I
Because you want, wait, is this not yours?
this is mine, but I also have the copy, physical copy because And water. So if you look at this, this is what is this? Which law is this? Newton's second law. Newton's universal law of gravitation. We started with this and we arrived at this. Okay? We started with this. What is this?
Kelvin's first law.
That's actually Newton's law. You just saw that and just repeated that?
Yes.
Okay. So that's Kepler's first law. It's orbit equation. Okay? You should be able to arrive at that. This is conservation of mechanical energy, total mechanical energy.
You want us for the first test?
Hmm.
Will we have like the first 2 rows? We tested on those.
This is conservation of angular momentum. Is this conservation of angular momentum?
Yes, it is.
No, it's not. It's just the definition of angular momentum. Okay? It's just the definition of angular momentum. H. This is more of conservation of total mechanical energy. Okay. Try to study this roadmap. It will tell you from where you.
So,
Yes.
how far up is information for the test? Up to this?
We'll talk about the test in just a minute.
Okay.
So you have V circular. Okay.
This is the third edition.
This is both in second and third edition. Second edition it happens to be just behind this thing, but in third edition it's there in the appendix B. So what is the time for circular orbits? What is the time required? How do you calculate the time required? Time period. T. What is 2 pi r?
360.
2 pi r is what? The circumference. Right? So if you have 2 pi r over V circular, what are you going to get? What are you saying? Just don't give me, just don't throw stuff based on, what is 2 pi r?
That's the circumference of the circle.
Huh?
Circumference of the circle.
Okay.
At any radius.
Huh? What do you get? What is circumference? What is it? What is that quantity? It's
Like this.
its length, its distance, right? So this is distance over what is this velocity? This V circular. What is distance over velocity?
Meters per second.
Huh?
Distance per time.
What?
D.
Distance. Hang on. Cool down and tell me what is distance over velocity. Just write it down and tell me. Don't do it in your head. You're not good to do it in your head. Just do it. Distance over time. Distance over velocity. Can you do distance over velocity?
Second.
What is it? So, what is distance over velocity?
That's time.
Huh? That's time. So, what is that? That is your time period of the orbit. You see it?
Yeah.
So don't try to jump, don't try to throw answers. You can do it by hand in your book if you cannot. So this is just simply distance over time. Okay? And T is the time period of your orbit, circular orbit. it's simply 2 pi r divided by root of r over mu. Circular orbit also called okay. So this is the energy equation. We have derived this. You can also see it there. The constant is this epsilon. Here, V square, we just use V circular, right? Because for a circular orbit it is. R over mu. You can say there is something wrong. This is mu. V circular is equal to mu over r, not r over mu. Okay. That's all.
Wait, I don't see it. B.
The square root still, isn't it?
Hmm?
It's still square root.
Square root is still there.
Okay. Yeah.
So you have r square, r comes down, mu goes. That's what we get r p over 2. This actually is mu over r. Mu over
It's
r.
true, that's it.
Implying minus
Oh, you still ended up with
Hmm?
your what T was equal to didn't change, did it? Even when you fixed it?
so v square is mu over r, right?
Yeah.
So I substitute mu over r here. It's mu over 2r minus mu over r, right? So this is half minus 1.
Okay.
It's
So,
minus half.
but the u over r part, I'm saying from the t, that didn't change. What your t is equal to. You always had 2 pi over square root of u.
Mm-hmm.
Okay.
So this is actually an important result. So here the question you're going to get for assignment is show that the total mechanical energy is not a function of the shape. So that the total mechanical energy is only a function We'll just do elliptical orbits and then we'll discuss a little bit about the exam. The elliptical orbits are the most common orbits, especially for a lot of the launches happen in the elliptical orbits. Most of them, unless it's a geostationary geosynchronous orbit, it's complete. Sorry, you understand geostationary is a circular orbit. I'll show you, I'll discuss with you why geostationary is a circular orbit. Has to be a circular orbit. Now, when we're discussing elliptical orbits, E varies from 0 to 1. Between 0 and 1, the orbits are elliptical. Okay? When we discuss elliptical orbits, I'll be using this figure a lot. See if you can make sense of this figure.
So ellipse or an oval. Ellipse with two foci.
Okay. Just look at this figure for a minute. Don't write anything. So what you see here is F. This is an ellipse, right? You identify the ellipse here. Okay. There are two foci, F and F prime. This is the F is the occupied focus. What does occupied focus mean? That there is a central body there. It's occupied. This, there is nothing here. So it is unoccupied focus. Where is the orbiting body here? The orbiting body is actually not shown here. But the orbit is this. Okay. What is the speed?
So what's the speed?
What is P? Yeah.
Oh, P from the central body is the closest to what's happening.
Right. It's
The closest distance from the central body to the orbit.
it's the point of closest approach, or it is the periapsis. P is the periapsis. Okay. This RP is the
Distance from.
distance, the periapsis distance. So you should try to get clarity on this. RP is the distance, P is a point. Okay? So this P is a point. Okay? What is B? This is simply minor axis. Okay? What is A?
A is the
Apparatus. And this RA is the
Distance.
position of the it's the position vector. So if you say even there is difference between position and distance. Distance means, so this RP, you see, it's actually a vector. It's in that direction, from this point to that point. It's this R at theta equal to, so RP is what? What is theta in terms of RP?
Say that one more time.
Terms of RP. It's
What is theta for RP?
a little bit more than zero. Well, E is a little bit more than zero, right?
No, E is fixed, right? For this orbit, if I give you an orbit, E is fixed.
RP or R?
What is theta? Theta is actually, if you assume that the orbiting body is here, theta would be the angle. Well, let me show it. This is what you have. And what we have done is, this is our P, correct? This is our F. If your orbiting body is here, this is our R. And theta is always defined with respect to this direction, the periapsis direction. Got it? So beta is a constant. Beta, don't worry about beta and alpha. Alpha and beta are other two angles. So your in strict terms, your eccentricity is actually that the ratio of alpha and beta, which is again some function of the semi-major and semi-minor axis. So don't worry about beta. Just think about this theta. This theta is this theta. So you see this body is orbiting, right? Because this theta is changing, this R is changing. For a given orbit, E will always be constant. But E can vary from 0 to 1 for various kinds of elliptical orbits. So what would theta be for RP? This is RP. Correct? RP would be h square over mu divided by 1 plus E. Because theta is
cosine is 1.
theta is 0, implying cosine theta is 1. Okay?
Wait, so So, how?
This is so this if the orbiting body is here, that is when this RP R becomes RP,
Uh-huh,
right?
right.
So now what is the angle?
Oh,
Theta is 0. Not almost, it is 0 actually.
between the body and, yeah, okay.
This P direction, what is theta? Theta is the true anomaly defined as the angle between the periapsis direction and the direction of the orbiting body. Okay, so this theta becomes 0, which implies cosine theta is equal to 1, and this just becomes 1, so you have 1 plus C. Similarly, what is RA? H square over mu divided by 1 minus E, because theta is equal to 180 degree.
That is equal to,
So,
180.
yes, so you have, if your orbiting body is here, this would be your RA, okay, and the angle would be theta equal to 180 degree. Which of this is bigger?
Alright.
Why is RA bigger?
Denominator is small.
Because denominator is small. So it makes sense why this is the biggest, this is the largest, RA is the largest. Okay.
Which one is the, you said RA is the largest?
We said this is the point of closest approach, right? So the distance between the central body and this point of closest approach, farthest approach has to be the largest. So you can see from this that this point of farthest approach is actually most away from this. All right, let's stop here. We'll just discuss a little bit about. We'll continue with this in the next class. But try to understand this. So what is semi-major axis here? Can you tell me the semi-major axis?
It's not really, it's the center of.
Right.
the horizontal.
It is this distance. This is A, right? The semi-major axis. A is different. A is the product of semi-major axis and eccentricity.
Product of semi-major axis.
Eccentricity. Semi-major axis is just the distance between center and periapsis, or center and apoapsis.
So if this is 0 for a circle,
A is equal to
0.
right. That doesn't mean anything. A is just it's the product of A and B. What is important is A. A is the distance between center and periapsis, or center and apoapsis. So can you say A is RP plus RA over 2?
Yeah.
It will always be there.
Yeah.
But you can't always say it's the product of the eccentricity and the, what's the other part you said? She said it's the product of eccentricity and
AE, that is AE. Forget about AE for now. Don't worry about it. Just understand this A. Whereas what is B?
what is it?
Yeah.
Why are you dividing it by 2?
This is
the semi-axis.
B.
The length, the semi-major
So this is B, right? This is me, A. We are talking about semi. A is always semi. B is always semi-minor, semi-major. So it is half of major axis. This is major axis, right? So your RP plus RA is this. This is how you have to make sense. It will all make sense. It is just geometry. It's just distance, points, and all that. So for your first test, which is 24th, none of this is going to be on the first test. First test will focus mostly on vector algebra. Largely what you did for your first assignment. Quincy, you have to see if you are feeling sleepy. This is for general, for anybody. You have to do something to ensure that you're not. You have to pay attention. If 8 out of 10 are sleeping, then it's my problem. If 2 out of 10 are sleeping, then probably there's something you have to work at. So try not to, because otherwise it gets difficult. So the first test will focus on vector algebra. You guys are responsible to wake people up when they're sleeping.
Yes, that's true.
Just hit them hard so that. Huh? So what we'll do is, for first test, it'll all be vector algebra. Is that okay? I may ask you expression for Newton's first law, second law, third law.
Can you give us some more problem practice?
Textbook.
Is it gonna be like the homework? Is it gonna be like the homework question? Is it gonna be like the homework question?
It could be like the homework.
But is it going to?
There's not going to be a problem.
For this, what formula sheet do you need?
R. Speaking of implementing AP equals
Huh?
R not. Oh man,
Yeah, just
Yeah, there will be one problem on relative motion.
one problem.
Relative
But
motion.
it's not going to be that long, right? Like the homework. Because that's impossible to do.
I may just ask you to do, it may just be derivation. Expression, not derivation. See, there's a difference between derivation and expression, deriving expressions. It's all kinematics. If I ask you to derive this, starting with, not for this test. If I ask you to derive this, starting with, or show me conservation of angular momentum, show me conservation of total mechanical energy. That is derivation. Expressions is just math. You can have a calculator.
So, can we do like problems on this, because looking at the variable calculation can honestly apply to an example. So,
We'll do problems on this. Yes.
okay, that was good.
So on Tuesday, what are you going to then for the test, or are you going back to this?
We'll do this.
Extra class on Monday.
You can have extra class.
Instead
We'll
of
do it.
Friday.
Huh?
Instead
Yeah, instead of Friday.
We can have it this Monday coming up.
So this Monday we'll discuss. You want to discuss homework?
Yes.
Okay.
Yeah.
We'll discuss homework, and I'll give you. If you want a formula sheet, I will request that you prepare one formula sheet and send it to me on Tuesday, so that I can take a printout and give it to everybody.
Oh, okay, so I don't want to get it.
Just give me one formula. I don't think formula sheet is actually required. It's
Just send me one.
Yeah, we'll send you one distribute
We can see if it works.
alright. Let's do this.
It's worth a try.
It's worth a try.
Check it out.
I don't think I order formula sheet, you guys, because especially not for this. It's the only thing you need to know is if you're going to put in conditions over there, I'm not going to allow it anymore. For example, what is the condition for the only formula you need to really know is dot product cross product. There is no other formula as such in there.
tell me how that number.
Maybe the back cab room.
That remember back, minus gas.
Alright, send me a formula sheet and see, let me see if it's required.
Okay.
You gotta send me one by,
Tuesday.
just send me one, okay, as a class. Don't send me. Good luck, please prepare.
Oh, the people out here.